All right, let's talk about 2D elements now. It's pretty exciting. We're going to be adding a new dimension now. We're going to see how the process we learned in 1D is somewhat extended to 2D, pretty much. The biggest thing here is, of course, we have now, instead of just u, we have u and v as our displacement vector. We also introduce the additional values of sigma y and the shear stresses, both for stress and strains. We have x, y values. And then the body force, traction vector, and elemental volume are now modified. The tractions and the forces are obvious. Here we're adding a thickness to that cross-sectional area along the z direction. When we add the second dimension, our force now has units of force per unit volume, and our traction force has units of force per unit area. Before it was unit length. The strain displacements are given by these equations. We have du, which we have actually already seen in a homework before, du dx, dv dy, and then the combination of those. Note that we have a du with respect to dy here, right? So that was the big trick in previous homework that we worked out. And the stresses or strains are now related by not just a single value like Young's modulus, but now we have a material matrix that we introduced in the very beginning of the lectures that includes our material properties, things like Young's modulus and Poisson's ratio. Of course, we're going to discretize this like we did in the 1D problem. So we have now our potato-shaped object, and we fill it with triangles. Just like in 1D, we had to discretize the shape here, so you can see the triangles fill in this shape pretty nicely. We do have these gaps that are left just due to discretization and the straight-sidedness of the triangles. So if we wanted to reduce that, we would refine our mesh here, and we could cut that in half, a sliver in half, and have a better representation of the geometry. So that would be revealed maybe through a mesh dependency study where you refine the mesh and see where your solution converges. It gets the same solution no matter what your mesh. And you have an idea of what kind of mesh resolution you would need. The other thing that's really important here is this numbering system. Okay, now you got to remember Q is what? Q is the displacement vector. And so what we're going to do here is storing XY data in a one-dimensional array. How do you do that? Well, you do that by the correct counting system. Okay, let me say that again. You're storing two-dimensional data, XY displacements, in a one-dimensional array. The way you do that is by using these incrementation labels. Okay, so you have Q2j minus 1 and Q2 times j. So let's consider node 1. 2 times 1 is 2, minus 1 is 1, and then 2 times 1 is 2. So you basically have this value for node 1, j is equal to 1, is equal to 1 and 2. Take node 2, 2 times 2 minus 1 is 3. Okay, so it incremented to the next position in the vector correctly, 3, and then 2 times 2 is 4, so 3 and 4. And so this numbering subscripts allow you to effectively store two-dimensional data in a one-dimensional array. And that can be confusing, but we're going to come back to it a couple times. All right, so I mentioned the straight-sided triangles. Next, after this, we're going to look at quadratic triangles, which can have sort of a curve in the edge. When we talk about displacements, we do an x and y, and I mentioned that we can store that. Well, each node, the formal way to say it is each node has 2 degrees of freedom. So you have x as 1 degree of freedom and y as the other. So the total degrees of freedom are the number of nodes times the degree of freedom per node. Okay, so I don't know exactly what we have here. Let's say we have 15 nodes, 15 times 2, so we're going to have a total of 30 degrees of freedom. So here's our global displacement vector, and you can see that it goes to the n, and here n is the number of degrees of freedom. So it's kind of confusing because this is not node 1 and node 2. That can be misleading. This is actually degree of freedom 1 and 2. So Q1 and Q2 both represent or are displacements of node 1. Okay, that is a confusing thing when we go to these higher dimensions. Now, just like in 1D, we had connectivity. Here are our connectivity details for this linear triangle, we have 1, 2, and 3 is our local numbering system. Notice we go counterclockwise, that's one thing. We have local degrees of freedom. For node 1, we have Q1, Q2, node 2, 3, 4, and 5 and 6 for 3. So these are the little q's, again, remember, similar to 1D, are called our local degrees of freedom. Here is the connectivity matrix for that. So if we look at element 1, we have 3 nodes, 1, 2, and 4, right? So let's go back here, 1, 2, and 4 for element 1. 2 should be 2, 7, or 4, or 4, 2, 7, or 7, 4, 2. It doesn't matter where you start, actually, as long as you go counterclockwise. So 4, 2, 7 is what they chose. So that's basically, these are the global numbers, just like in the trusses, and this is the local numbering. So you can see how the process is very similar as we extend up in higher dimensions. There's an element displacement vector just as there was in the 1D case. And so we had Q here, went to the degrees of freedom. For the local elemental vector, it only goes up to 6 because we only have 6 nodes per element. So little q is the size of 6. So we're seeing that the element has all the same ingredients as in the truss problem, right? Both linear and quadratic truss. Connectivity, numbering, local and global values. And so the displacements inside the element need to be represented in terms of nodal displacements of the element. And we're going to talk about the concept of shape functions and systematically develop these interpolations for the constant strain triangle. That's actually what we call it. I'll explain why we do that later. But they can be linear or they can be quadratic, just like the truss. And so the form of our formulation remains very similar. The equations inside change. Okay, so we're going to end it there, that short introduction of the constant strain triangle. We're going to continue filling in the details of that as we go in the upcoming lectures. In the next lecture series, we're going to actually pause and do a short exam just to make sure we got everything firmed up in terms of the theory of the finite element method. You're starting to see that in 2D that we basically are using very similar formulations in 2D that we did in 1D. And so it's really important that we understand that basic formulation as we build on it in 2 and 3 dimensions. So we're going to take some time to do that in the next lecture series. Application 7 would be following. That's on bolt loading, and that allows us to really save time when we're modeling bolts. We use a lot of bolts and connectors and fasteners, and so this really focuses on that. It's also a multi-lecture, multi-app application in the sense that we're going to do a couple different problems with this bolt loading. So that's upcoming also. So we'll wrap it up there, and I'll see you next time.